So number of times we come across a situation in which a shaft is subjected to a multiple torque here. So we have a electric motor here, which one is, and this assembly shows an ice cream maker has a shaft with a pedal. This one is pedal 1 and the pedal 2, which is driven by the electric motor from the bottom. Due to the ice here, the torque is developed on the pedal 1 and pedal 2 is equal to 2.5 Newton meter and 2.5 Newton meter. So in this type of problem, the shaft is subjected to multiple torque, and whenever the shaft is subjected to the multiple torque, we are normally interested what is the shear stress developed if we have a shaft of a same diameter or of different diameter, and what is the total angle of twist. This type of problem will come in two categories, in which both the ends are free or one end is fixed. In that case, we can find out the total angle of twist by using the simple 2 equation, and that is called as statically determinate. That is the number of equations given by the static conditions are sufficient to find out the number of unknowns. That is called as statically determinate. And the second situation is that we have a both ends are fixed end, and we'll apply here torque. In that case, we have to find out what is the angular deformation between the each section here. That will be called as statically indeterminate, because the equation of a statically equilibrium will not going to solve the problem. So that concept we'll discuss later on. Right now we'll discuss here one problem of a shaft in which we have a multiple torque are applied. Either both ends are free or one end is fixed. That is first case we'll discuss is a statically determinate problems. So consider here a shaft, a step shaft basically of diameter equal to d1 and diameter equal to d2. At free end we are applying a torque is equal to Tc, which one is a clockwise torque, and at B we apply a torque equal to Tb. Length of the first shaft is equal to L1, second shaft has a length equal to L2. At end A we have a fixed support. So at point A the shaft cannot be twisted, so we are here the value of theta A will be equal to 0. Theta B we can find out with respect A. We have theta B with respect to A will be equal to theta B minus theta A. In this case the value of theta A will be 0, so theta B with respect to A will be same as equal to theta B, and then we'll calculate what is the total deformation of C with respect to A. So first we calculate here the total deformation of C with respect to B. That will be equal to theta C minus theta B. And theta B we know from the previous equation. We'll substitute here and we can calculate here the total value of theta C. Theta BA we can calculate here what is the torque acting on the length L1, that is for shaft AB. So this value we can calculate using the angle of twist, that is we have TAB multiplied by length AB divided by different materials. Then we have to take the modularity of shaft AB multiplied by the polar moment of inertia of the shaft AB. Similarly, theta C with respect to B we can calculate using the same formula, that is we have torque acting on the shaft BC multiplied by length of BC divided by the modulus of GT of BC multiplied by polar moment of inertia of BC. In this fashion we can calculate here the total deformation of C with respect to A, because A is a fixed, so absolute value we can find out here. Main question is that what is the torque at BC and what is the torque acting on the shaft AB. That analysis can be done by drawing the torque diagram or FBD analysis. So right now we have focus is on the angle of twist when the shaft is subjected to multiple torque. So for reference we'll draw here horizontal line, and because of a twisting moment on the shaft AB, this line is get twisted. This line you can visualize as this line, which one is a shear strain is produced, and if I draw here a line radially towards the center, so this line I will draw radially towards the center. In that case initially we are at the center, that is origin, so this line we can visualize here as A, that is the point A, and the point B will be at the same level, but after you apply the twisting moment to the shaft AB, the B has been shifted to the new position equal to B prime. In that case we can calculate what is the angular twist in the shaft AB. So this one is a angular twist of B with respect to A is written as theta B with respect to A. And we have to calculate the value of theta B with respect to A as theta B minus theta A. Now theta A will be equal to 0 because at A we have a fixed support. So theta A will be equal to 0. So theta B with respect to A will be same as equal to theta B. Now we'll draw here a reference line, that is this dotted line, which one is a horizontal, and we'll consider separately the twist of C with respect to B. In that case, the point C will shift from this position to this position, making an angle here. So this angle will be here, you can visualize in this figure. So this angle formed here will be same as equal to theta C with respect to B. Now theta C with respect to B can be written as theta C minus theta B. And from the previous equation, we know the value of theta B, so we can find out here the value of theta C. Now theta BA and theta CB, you have to find out what is the torque acting on AB. That will be equal to torque multiplied by length divided by J divided by G. All these data you have to collect for the shaft AB. And this value of theta C with respect to B you have to again calculate using the same formula, that is TL divided by J divided by G on the shaft BC. So clearly here the value of theta C as seen from this figure will be the total deformation of C with respect to A. So this one is total deformation of C with respect to A. So absolute value of theta C, that is the total deformation of theta C with respect to A, twist for B with respect to A plus twist of C with respect to B. That will be same as equal to TL of JG for the shaft AB plus TL by JG for the shaft BC. So whenever we have a multiple torque, then we can calculate the value of theta as summation of TL by JG. If you have a uniform diameter, then you can take out J and G common if the material is same, and then you can simply add here as a T1 L1 plus T2 L2 by labeling the different shaft as 1, 2, 3, 4. Only question is to be answered is that what is the torque exerting on the shaft AB and the shaft BC. We can have two approaches here. The first approach is that you draw the torque diagram and you can consider the clockwise torque as a positive and anti-clockwise as a negative, or you can take any sign convention as you want, but you stick to that sign convention. If you consider the clockwise positive, then throughout the multiple torque you take the clockwise positive and anti-clockwise is negative. Always start the diagram from the free end and close the diagram at the fixed end. You have to start at 0 and end at 0, then the torque diagram will be complete. Second case is that you can draw the FBD at a various section where the torque is applied. Even the torque is applied here, you have to take one more section and you have to develop the FBD, and you can calculate the torque in each section of the shaft. So I will discuss both methods here, that is the torque diagram as well as the FBD method. Now this concept is known to us, that is total angle of twist is just obtained as a theta 1 plus theta 2 plus theta 3, whatever the steps are given to you. So let's consider here a torque diagram. Here we have at point C, concentrated torque is applied equal to TC. So you have to draw here a vertically upward line representing this torque, which one is a clockwise torque. This torque is also clockwise torque. So at C, show the magnitude wise arrow of TC. Then between B and C, no torque is exerting, so the torque values remain constant. This concept is same as the SFD diagram, shear force diagram, that we have already discussed. So since there is no torque is acting from B to C, the torque is remain constant over the section BC. So we have torque on the section BC will be same as equal to TC. Hence we can calculate here theta of C with respect to B using the torque for the section BC multiplied by length divided by J divided by G for that particular section. Then you come to at point B. At point B, there is suddenly a torque is applied, that is a constant torque is applied TB clockwise direction. So you have to move vertically upward by a distance equal to TB. So since the TB is a clockwise here, as well as TC is also clockwise, so you have to move vertically upward. This value is same as torque for BC, which is equal to TC value. Now since we are moving vertically upward and between A and B there is no torque acting, so torque is remain constant. So this torque is the previous two value. So this one is the torque for the section AB. So we have torque for AB will be equal to torque at B plus we have torque at C. And then from this point you have to move vertically downward, that will be the reaction torque. So in this case we have reaction torque is TA is equal to TB plus TC, but since you are moving downward it will be counterclockwise. This is called as reaction torque. So we got both answer here. We got torque acting on AB as well as torque acting on BC. So this one is called as torque diagram. Second approach is that we can draw the FBD. For FBD you have to consider here first this section, and for this section is applicable to B except the concentrated torque applied to point B. So this one is torque C and this one is point B and this one is point C. Now the total torque applied for BC can be calculated using the summation of the total torque. So in this case only one torque is applied, so we have total torque for BC will be same as equal to TC. Then you can take here one more section here and you consider the complete FBD. So you have to consider here from A to B and then from B to C. Then you can show here one torque equal to TC. Then you can show here second torque equal to TB. Then for the portion AB we can calculate torque. So this torque will be torque AB is simply equal to, both the are clockwise, so you have to simply add them, that is the value of TB plus TC. So either you can go by FBD or you can develop the torque diagram. Once you develop the torque diagram, you know what is the torque is acting on AB and BC, and in this position we can calculate here the total angle of deformation. And even we are knowing the value of torque acting on each section AB and BC, so torque is equal to pi by 16 d cube into tau, that is the shear stress. We can calculate what the maximum shear stress developed in AB as well as in BC. So either you can practice for FBD or you can practice for torque diagram. As far as me is considered, I will go for the torque diagram. This one is very easy to develop. This is slightly time consuming technique because every time you have to draw the FBD. Now we'll just practice here how to draw the torque diagram. Now first of all at point D we have constant torque equal to 100 Newton meter. So this one is a clockwise torque. Then this will be counterclockwise torque. And this will be clockwise torque. So you have to first fix up here the sign convention. So we have fixed up the clockwise torque equal to positive value. And the counterclockwise you will take as a negative value. Then we have point A, B, C, D. So we'll consider one section AB, second is BC and third is CD. So I am drawing here A, B, C, D. Length I am not interested. I am just interested to know what is the torque is acting on AB, BC and CD. This one is clockwise and clockwise is taken positive. So we will move vertically upward by torque T3. And this value of torque T3 will be same as equal to 100 Newton meter. Between C and D no torque is acting, so the torque is remain constant. For section CD we have torque is equal to 100 Newton meter. So this height is proportional to 100 Newton meter. Then at point C a constant torque of 300 Newton meter is acting counterclockwise will be negative value. So this value will be equal to 100 and this is total 300, so you have to move vertically downward by another 200. So this total value corresponds to here value of 300. But this you have to take as a negative value because you are moving downward. Between B and C no torque is acting, so the torque is remain constant over the section BC. So this torque is torque acting on section BC is just the sum of the previous two, that is minus 300 plus 100, that equal to minus 200. Then at point B one torque acting is equal to T1, which one is 600 and is clockwise. Clockwise is positive. So already we have 200 down, so we will move upward by 400. So that the total distance will be covered is equal to 600. So this value will be equal to, total value is 600. And then from A to B no torque is acting, so torque is remain constant. So this one is representing the torque for AB. Now previous value is minus 200, this one is positive value because it's a clockwise. So minus 200 plus 600, that will be equal to 400 Newton meter. And then we have reaction torque will be equal to 400. So in this case we have reaction torque TA is equal to 400. We are moving downward, means negative value. Negative means counterclockwise. So this one is counterclockwise. And hence we can calculate here what is the theta 1, theta 2, theta 3. So this one is shaft 1. So in this case we have T1 value is equal to 400. This one is shaft 2. So we have T2 is equal to minus 200. You have to take the minus, and this one is a positive value equal to 400. Then only we will get the exact answer. And this value will be taken as positive. This one is T3, which is equal to 100. And you take this value as positive. This value you have to take as negative, and this value you have to take it positive. And then use simple formula to calculate the value of theta, which is equal to TL by J into G. Now this time the J and G is constant, so we can take it outside, 1 by JG. What is left is T1 L1. So we have T1 and L1. So we have T1 L1 plus T2 L2 plus T3 L3. T2 you have to take is negative value. So we have 1 upon J by G. T1 is equal to 400 Newton meter. So we have 400, and we have distance is 15 cm, that will be equal to 150. Mm will write multiplying by 1000, all multiply here by 10 to the power 3. Then we have T2 value is minus 200, so we have plus minus 200. Length L2 is equal to 20 is 200. Plus we have T3 is positive value is equal to 100, and L3 is equal to 300. All this you will get the total deformation of point D with respect to A. A is fixed, so theta A will be 0. This one is absolute value of theta D. Now consider this numerical here. We have given here the number of torque. There are total 5 torque is acting in the segment AB, BC, CD and D. So you have to find out here what is the torque in AB, torque in BC, torque in CD and torque in D. Again you have to finalize here the sign convention. So this one is a clockwise, this one is clockwise, this one is counterclockwise, this one is clockwise, this one is counterclockwise. Now we'll start with the right end, and we'll take the value of clockwise as a positive value, and counterclockwise we'll take as a negative value. So first you have to rise by 800. 800 is a positive value, so we'll show this length of arrow approximately equal to 800 Newton meter. There is no torque acting between D and E, so this value remain constant. So this value remain constant, and this one is the torque acting on the shaft DE, that will be equal to positive 800. Then suddenly at D we have again a clockwise torque equal to 500. Clockwise is positive, so you have to move vertically upward. So this vertical distance will be same as equal to T4, which is equal to 500. And between C and D there is no torque acting, so it will remain constant. This value represents the torque for CD, which is equal to the previous 800 plus 500, that will be equal to 1300. Then at C we have a counterclockwise torque is acting equal to 800. Since counterclockwise is negative, so from 1300 you have to move downward by 800. What is left is 500. So T3 is equal to minus 800. So this value is minus 800 Newton meter. Then B to C no torque is acting, so this value is remain constant. previous value was 300 and minus 800. So the torque acting on the segment BC will be equal to 500. So we come at point B. At point B, we have 500 Newton meter is clockwise. So this value is 500 and again 500. It means that it will be equal to 1000. So this value is equal to 500. And between AB, no torque is acting. So that will remain constant. So this one is torque on the segment AB. We have previous value is 500 plus 500. That will be equal to 1000. So this one is very simple procedure to know the torque on each segment. And finally we have 1000 Newton meter counterclockwise, that is negative torque acting at point A. So we'll close this diagram. So torque diagram must start at 0 and must end at 0. That is only the cross check in the torque diagram. And otherwise you can draw the FBD by drawing here number of multiple segments. Naturally you have to do here 4 FBD and therefore it is a time consuming technique. So avoid that method and use the torque method. Again here all the value of the torque is positive in all the segment, that is all the 4 segment we have theta value is positive value. So these are the situations when either the one end is fixed or both end is free. That is called as statically determinate problem. So very easily we can develop the torque diagram. We are knowing here what is the torque acting for each segment. Finally we can find the value of theta. Now again here it is a common shaft, so we can take out here 1 by jg common and then you can simply write as shaft 1, shaft 2, shaft 3, shaft 4. So it will be simply the product of summation of Ti, Li. And your angle of twist can be obtained. And even you are knowing here what is the torque acting on each segment, you are able to calculate here where the shear stress is maximum. Now here the maximum torque is on segment CD. So on this portion we have maximum value of the shear stress. Torque is directly proportional to shear stress, because for solid shaft we have torque is given as pi by 16. We have a same diameter equal to d cube. So from this equation we can conclude here is that the shear stress is directly proportional to the torque. And the second question is that where we have minimum shear stress, so minimum value of the torque is between segment BC. So at this point we have minimum value of the shear stress. Or they can ask you what is the ratio of the maximum shear to the minimum shear. Again you have to draw the diagram, identify where we have maximum torque, minimum torque. Correspondingly you can calculate here what is the ratio. Now this ratio of torque max and tau minimum is same as equal to the maximum torque and the minimum torque. So any time you have to find out the ratio for uniform cross section of maximum shear stress to the minimum shear stress, that will be same as equal to the maximum torque divided by the minimum torque. This type of objective questions are expected on multiple torque. In the next video we'll going to check how to solve the problem in which both the ends are fixed and the shaft is subjected to either single concentrated or two concentrated torque in between the two fixed support. That is called as statically indeterminate problem. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.